Sora is one of the most advanced text-to-video generative model published by OpenAI. In this video, we are going to explore how Sora is trained, how training data looks like, and what are all the safety measures OpenAI have taken before they're going to publish this model for the general public. So let's begin this exploration. Before we start understanding Sora in detail, let us have a quick tour of some of the user prompt and the video generated by the Sora model which are published by OpenAI. Okay, so Sora is an AI model that has following key features. Number one, it can create realistic and imaginative scenes from text instructions. Number two, in addition to being able to generate a video solely from text instructions, Sora can take an existing still image and generate a video from it, animating the image's content with accuracy and attention to small detail. Number three, Sora can also take an existing video and extend it or fill in missing frames. Extending videos can be forward or backward in time. Number four, connecting videos. We can also use Sora to gradually interpolate between two input videos, creating seamless transitions between videos with entirely different subjects and scene compositions. Number five, image generation capabilities. So Sora is also capable of generating images. Then interacting with the real world is very important. Sora can sometimes simulate actions that affect the state of the world in simple ways. For example, a painter can leave new strokes along a canvas that persist over time, or a man can eat a burger and leave bite marks. These are not the only features for sure. I'm confident that OpenAI will release more features through this Sora model. So we talked about the key features of Sora, which is published by OpenAI. Now let us try to understand how this Sora model is trained. And to understand that, let us try to understand the training data itself. So the training data look like this. So you have T and V, a pair set where T is the text caption of that video V. This process begins with a collection of a vast array of captioned videos from the internet. Subsequently, these datasets are processed through a data pre-processing pipeline, which meticulously pairs each video with its corresponding textual caption, thereby creating a structured dataset essential for model training. So now we understand how the training data looks like. But we also know that machine learning algorithms fundamentally operates with numerical inputs. Like in large language models or text generation models like GPT, this text data is converted into numerical format called tokens, which is numerical representation for word or subwords. In Sora, which is video generative model, these training videos are converted into numerical format called visual patches. Patches are highly scalable and effective representation for training generative model on diverse types of videos and images. At a high level, videos are converted into patches by first compressing videos into lower dimensional latent space and subsequently decomposing the representation into space-time patches. Given a composed input video, they extract a sequence of space-time patches which act as transformer tokens. This scheme works for images too, since images are just videos with a single frame. This patch-based representation enables Sora to train on videos and images of variable resolutions, durations, and aspect ratios. Having delved into the nature of Sora's training data, it becomes evident that its proficiency and precision are basically linked to the caliber of its training inputs. Training on highly descriptive video captions improves text reliability as well as the overall quality of videos. Therefore, to ensure the training data meets the highest standard, a caption generation model was initially developed. This model plays a crucial role in crafting detailed captions for video data used in training. With the availability of precisely paired training data sets, Sora goes its subsequent phase of training, further refining its capabilities. Let's try to delve some more deeper intuition about these processes. To train this captioner model, transformer architecture is used. We start with a deep neural network algorithm, a piece of software code. Training data consists of paired set of text caption and corresponding video. The algorithm's primary function is to learn patterns within those sample videos and related caption and store the learned patterns in the memory and produce a trained captioner model. Then this model is tested with a new video input to check if it is able to generate high quality caption. Even for the videos for which some sort of captioning was available, but those videos are also sent through this captioner model to recaption. So this process is called recaptioning. Now let us try to build an intuition on the stage 2 where the training of Sora model happens. Transformers have demonstrated remarkable scaling properties across a variety of domains, including language modeling, computer vision, and image generation. So Sora is also trained on a diffusion transformer. So we start with a deep neural network algorithm, a piece of software code, and then training data consists of paired set of text caption and corresponding video patches. The algorithm's primary function is to learn patterns within those training samples and store the learned patterns in memory and produce an output called trained model. In this case, it is Sora. During inferencing, a GPT text generation model is placed before Sora. This model turns short user prompt into longer detailed prompt or captions that are then sent to the video model Sora. This enables Sora to generate high quality videos that accurately follow user prompts. So I hope we were able to get a good intuition about how Sora model is trained. We all know that these models, if not used diligently, can cause harm to the society. OpenAI recognizes the critical importance of safety in relation to the content generated by Sora. Therefore, they are proactively implementing numerous safety measures before releasing Sora for general use. So let us try to understand what are all the safety measures being implemented in Sora by OpenAI. As stated by OpenAI on their release page of Sora, apart from many safety measures, there are two important checks. Number one, text classifier. Text classifier will check and reject text input prompts that are in violation of their usage policies, like those that request extreme violence, sexual content, hateful imagery, or the IP of the others. In case request is not rejected, then it passes through this gate and reaches Sora. Then Sora tries to generate a video as per user prompt. But this video is not yet sent to end user. This video has to pass through another gate, which is image classifier. Image classifier is used to review the frames of every video generated by Sora to help ensure that it adheres to their usage policies. In case the generated video fails to adhere the usage policy, then this video is rejected. Otherwise, generated video is made available to the end user. In addition to these checks, they are also engaging policymakers, educators, and artists around the world to understand their concerns and to identify positive use cases for this new technology. They believe that despite extensive research and testing, they cannot predict all of the beneficial ways people will use this technology, nor all the ways people will abuse it. That is why they believe that learning from real world use is a critical component of creating and releasing increasingly safe AI systems over time. There are some more key features: sampling flexibility, improved framing and composition, image generation, we already talked about, emerging simulation, video to video editing, connecting videos, and so on. So to conclude, OpenAI Sora presents both exciting possibilities and serious challenges. Embracing its potential while mitigating its risk requires a multi-pronged approach that involves collaboration between developers, policymakers, educators, and the public. By prioritizing transparency, ethical guidelines, and public education, we can ensure that Sora becomes a tool for good, empowering creativity and knowledge while safeguarding individuals and society from their potential harms. Thank you.